Hey, this is the second tutorial that I'm doing to describe how the Catia FEA program can be used to do a simulation of a 2 degree of freedom system for free vibration where initial conditions are specified. Now, I call this video series the killing a fly with a cannon because these type of problems are so elementary that really need not be done with a sophisticated embedded FEA program in the Catia program. Okay. Now, however, my philosophy is that if one is to make sure that they know how to use FEA for dynamic problems, they should also be able to solve such simple cases. In the first video that I did for the 2 degree of freedom system, I showed you how to extract the natural frequencies of the system. There were quite a few videos prior to that, and they dealt with a single degree of freedom situation, and therefore there was only one natural frequency that could have been extracted. Here, this is the 2DOF, 2 degree of freedom involved, and therefore there are two natural frequencies that can be extracted. Now the information is given here, and here, by the way, Catia uses the linear dynamics capabilities, functionalities, and therefore the first step in the dynamic calculation must be extracting natural frequencies. Now, here I'm saying, okay, why don't we take the mass M1 and move it before vibration taking place, move it by an amount that's given here, 0.001 meter. And of course, if you do this thing slowly, x2, mass 2, will also move by the same amount. So let's say that this particular problem, the initial conditions are very special. Both the mass 1 and mass 2 have the same initial displacement. Now, if these are different, the situation changes, and I challenge you to go and solve the problem for that case. The other thing is that we are assuming that this is released from the rest condition. In other words, once you displace mass 1, and therefore, if it's done slowly, mass 2 goes with it by the same amount, then we release them without giving any initial conditions. Now, in the first video, I showed that this problem has two natural frequencies, and the natural frequencies in radians per second are given here, and these are in hertz. Also, I told you that I will be using spring rigid type of connection to essentially simulate the effect of the spring. Now, the initial movement to that position 0.001 of mass 1 and therefore mass 2 is done very slowly. So we slowly over 4 periods of the smallest natural period. So remember that here the period, there are 2 periods involved. I took the smaller one, 3.14. I believe that's the smaller one. Oops. That is the smaller one. So let me see for a second. Yeah, that's associated with this frequency. Okay. And let me see for a second. Where are we here? I'm doing this movement of mass 1 and therefore mass 2 over 4 periods associated with that frequency. And then we release it. And then, so this is the force, displacement times the stiffness of spring 1. That is the force that's needed to displace mass 1, and then drop the force to 0 and let it stay 0. So this becomes a natural free vibration. Okay. By the way, we are assuming that there is no damping here, but even if there was a damper involved, you would do the same type of thing. Now, there are several slides here which are actually taken from my vibrations course, And I just put it here to show you how I arrive with the analytical solution of this problem. So here's one slide. This is where you do the decoupling using the modal coordinates, okay? And you calculate the coefficients involved based on the initial condition, okay? And finally, you do the reverse transformation in order to find the solution. So the solution to this problem, the solution of displacement of mass 1 and mass 2 are given by these two expressions, okay? So if you plot them separately, these are the analytical solution. When we do Catia, we will see that here's the analytical solution. We will see that initially over the 4 period, of course, the displacements are gradually increasing up to the point 0.001 meter, that's this point, and then release it. And this is going to be the stage of free vibration. So the analytical solution should be compared with this portion of the graph generated by Catia, not this one, because this is just to impose the initial conditions, initial displacement. Mind you that in some packages, initial conditions can be specified directly, but not in Catia. There is no provision for specifying initial conditions in Catia for dynamic problems. And the reason is that the philosophy of the FEA, embedded FEA program in the Catia was to look at the steady state response, but not the transient response that dies out because of the initial or because of the damping. Okay, so let's go ahead and do this problem. I suggest that you also look at the first video, but I'm going to be repeating that to some extent. But there we are. Okay, so let me create 2 points here. One of them is that the global origin, the other one is 100 millimeters away. That's to place my middle, basically, mass. And then another one, 200 millimeters away. Okay, and then create a line between this point and that point, and another line between this point and this point. And because I have to mesh these with beam elements, there is no way out of that. Here you have to create these with beam elements, because that once you create the beam element, then you can create your spring elements later. Okay. So first of all, I don't want duplicate nodes in the middle. So why don't I go ahead and basically join these two lines. That means that when a mesh is created, the point in the middle is not going to be a duplicate node. That's the only purpose, the only reason behind this joining. This joining could have also been done in the mechanical design, wireframe, and surface design, but that's right, I did it here. And I mean, obviously, you can go, if you want, you can go back to part design, but I'm not going to do that because there's really no reason. Let's apply material to that. Metal, aluminum on that part, and we're going to reduce dramatically the stiffness and the density of this dummy material that we put in there. So 0.1 is going to be the Young's modulus, 0.1 Pascal, which is pretty much nothing, and 0.1 kilogram per meter cube, which is nothing, even lighter than air. So, all right. Once we do that, then we're going to go to generative structure analysis. We're going to have to mesh this thing with beam element. Now, I will do a static case first because I want to debug the situation, debug any possible errors. So let me see now. Yeah, here's the beam element. And when we select this, because it's joined, it's going to do it completely, mesh it completely. And I want minimal mesh. It doesn't matter what number you put in here. If you say minimal mesh, it just gives you 2 elements. One from the wall to the middle point, and another element from the middle point all the way to the end. Okay? In fact, we can check that. Right-click mesh visualization. There's going to be 2 elements here. This is going to be element number 2, going between nodes 3 and 2. And this is going to be element number 1, going between nodes 2 and 1. Notice that there is no duplicate node regardless of how you approach this middle point. All right, so let's deactivate this. And now we have to create a section. This section plays no role. It's a dummy section, basically. I just made it circular to avoid going and selecting an orientation point. Circular is fine, and it doesn't matter what the radius is. This does not come into the calculation. But you have to do that, because otherwise you cannot go ahead and create spring elements in Catia. So let me hide these points first of all. Hide these points, because I don't want to end up putting a restraint or a load on the point. Catia will take it, but it will not run. It says that point is not a geometrical, is not a finite element entity. Now, we're going to create two connections. This is the trick that you have to do. General analysis connection. The first connection going between this point, this vertex, and that vertex. Oh, not the edge. Oh, yeah. Okay, good. And another one between this vertex and for the second component, the vertex at the very right-hand side. So we have created two connections here. The first one is that one, which is going to have a stiffness of 24 Newton per meter. The second one is this one, which is going to have a stiffness of 3 Newton per meter. Okay, now we go to the distance connection property. See that? Distance connection. This is the distance connection property toolbar. Okay, and we go all the way to the end, which says user-defined distance connection property. You click on it. So I want to use, well, let me start with this first one, the first connection that I created. See this one? You select this, and then immediately it grays these out, and I'm using spring rigid. So you click on the wrench, and you put a stiffness of 24 in the direction Y. Okay. And then you click on it again, select the second connection. Again, spring rigid, select the wrench, and make this thing 3 Newton per meter. Now notice that these kind of things could not have been done without meshing those lines with the beam elements. Just that it just doesn't take it. You can't do it. Okay, good. Now apply the restraints. So restraint is right here. This one is clamped. This middle node, middle point, does not move. It does not move any direction but Y. And the other one, same thing. Now, because I want to assess the possibility of having made any mistakes, I'm going to put a static load of 1 Newton here, force right there at this point, 1 Newton direction Y. And if I run this thing and solve it and look at the displacement, maximum displacement should be 375 millimeters. That means that I did not make a mistake. Effectively, what I'm doing here is that I'm saying that if I apply a load of 1 Newton here, these two springs are in series. Find the stiffness of it and divide it by this force applied. You're going to get 375 millimeters. So let's check it out. Okay, so look at the displacement, 375 millimeters. So I didn't make any dramatic mistakes here. We don't need this static situation for this problem. Actually, we do need it, but I'm also going to do something else here. Let me also put a load. Now, notice that I put a load of one Newton here, okay? And by default, this is also going to be 1 Newton. So in fact, what I will do is the following. I will actually delete this load. I'll delete this load, or let me do the following. Instead of, okay, I should have thought about this thing a bit earlier. So let me deactivate this plot. Okay, good. Now, double click on this load, because at the end of the day, my load is at this, with this plot, my load is at node at the middle point, not at the end point. Okay, so I'm gonna remove this, remove the support, and I'm gonna select this point and put one node, Newton on it. If I run it, obviously, what's going to happen is that the stiffness of 24, 1 divided by 24, I'm going to get the different displacement. Let's try it. Let's try it. Okay, good. If you look at the maximum displacement, obviously it's going to be different, right? Because if you put in 1 Newton at this node, you're going to have 375. Because it has to fight two springs. If you put 1 Newton at this node, it's going to have to fight only one spring with a stiffness of 24. Okay, so 1 divided by 24, 1 divided by 24 is going to be this one times 10 to the minus 3 in meters. Okay, so it is correct. Good, but I do need this load here, because later on when I do free vibration, I have to drop this force to 0. I have to move this thing by 1 millimeter, or thousandths of a meter, and this is going to go with it, because it's, I'm going to do it very slowly and then drop it. It's going to become free vibration. Okay, so far so good. Now we're going to insert a frequency case with the reference restraints from the static case that we just did. This is the static case that we just did. Here's the reference restraint. Good. Now let me remind you that if you double click on this frequency case solution, it's asking for 10 frequencies, but we don't have 10 frequencies. We have only two. We have only two modes. So we say, oh, 2. Otherwise, you get an error message, and I showed you that error message in the previous video. Okay, so masses. Let me not forget masses, because I did forget it the first time in the first video. So here is the distributed mass on this point. It's going to be 9 kilograms. And another one, but at this node, it's going to be 1 kilogram. And that's pretty much it. If I run it, I'm going to get two frequencies, and those frequencies are 0.225 and 0.318, I believe. These are the things that I showed you in the slide. Yeah, 0.225 and 0.31. So frequencies are extracted correctly. Now, we're going to insert a transient dynamic response. And for the reference frequency case, we're going to use the one that there's only one frequency case that is right here, and I'm going to select it, and we say OK. And this is load excitation, by the way. It's not restraint excitation. Good. Now, let's check a couple of things here. I want to do the simulation over a 32 and a half, what is that? Let me over a 30, yeah, okay, let's make it 32 and a half second interval. So the first 12, which is going to be 4 natural periods, is going to be just stretching this thing. And then the remaining 20 seconds is going to be the free vibration. Okay, so here's what we're going to do. Let's go back here. Double click on this. Don't go all the way to 10. Go all the way to 32.5. Okay, and number of steps. Now notice that if you put a small number here, you get numbers that maybe the plot may be jagged, results may be inaccurate. Let me leave it the way it is, and then we're going to come back and change this, because we have no idea what it should be. Let's see it at 220, and then we come back and see what the effect is. Good. Damping, double click on it, click on the wrench. We don't want any damping. By default, Catia puts 1% damping. Okay. And for load excitation, we need that Excel sheet that I showed you. We need this plot. Okay. Now, the problem is that I have not imported this. So let me go ahead and import it. First of all, as far as selected load, selected load, it's that thing that I put in the middle. Remember, I went and changed it right there. But then it also needs a modulation. In other words, force versus time. And I don't have it. So cancel this. And let's go and, first of all, read that Excel sheet into the program. So time modulation, that's what I want. It says, where is it? So we click on it, and it is it's this one, F1 versus T. Actually, it should be 4T1. Doesn't matter, it's just the name of the file. You can check it out. Let's go ahead and plot it. It's there. The modulation has been created. Yeah, modulation has been created, imported actually right there. Right click, generate 2D plot. It better go to 12.5 all the way 0.024 and then drop to 0. So that is good. I'm going to close this. It's important. Now we go to the load excitation. For the load, we select that force that I applied, 1 pound, dummy pound that I applied here. And for the modulation, I go and select this time modulation that I imported. And the scale factor is 1. That's pretty much it. So here's what happens. If you put the cursor here, right click and say generate 2D display, next, and finish one plot only. It says, okay, where are the 2 points that you want to plot something about? So first of all, let me minimize this. Go here, and I want to select these 2 points, but it won't let me do that. But let me hide some of this stuff. I put the cursor here, you can see that. I put the cursor here, hide this. I put the cursor on it again, hide it. Now I can go and select this point, okay? But do the same thing there, hide, hide. Okay, so for the first node, I'm going to select this, okay? First node means the middle node. That's what I mean. Node 2 is the middle one, okay? And make sure you say add. And then again, you select this guy. This is the node at the end, the mass 2 basically. And then add. And I don't want displacement translation X and Z. I want translation Y. And we say OK. So that plot has been generated here. Double click on it. And notice that it's going to be fairly jagged. You can see that. And that has to do with that number of sections that we left it at 20, the default. Let me close this and cancel that and close this. Go back here to the transient dynamic response. Instead of 20, make it 200. I'm going to make it 2000. In reality, what you should do is you should gradually increase this thing from 20, say, to 200, look at the results, then to 2000 or 1000, look at the result. Once things don't change that much, you know that you have selected the appropriate number or reasonable number. We say, okay, now once again, I double click on that plot right here in the tree, double click on that. You see that? Jaggedness is gone. Now, this is the plot of amplitude, not the positive and negative value, because remember, this is sinusoidal. It goes positive, negative, etc. So you put the cursor here, right-click, format, real. You see that? Good. Now, the one thing that I realize is that it also plotted the component Y and Z. I'm going to clean that up in a second. And the unit is meters, so right-click. Let's say that we change this thing, we'll put the cursor on the white area of the plot, right click, options, and change that from MKS system to the default options defined, which I believe I use millimeters for displacement. You see that, it changed to displacement? Yeah, so this is to be compared with that plot, except that this goes from 0 to 20, and what I have here goes from 0 to 32.5. But the first 12.5 seconds was actually to put this thing in the right position. So the actual comparison should be between 12.5 seconds to 32.5 seconds and 0 to 20. And these are pretty much in agreement. You can see that. They look qualitatively the same, number-wise are the same, and good. Now, Let me do one thing here. I'll go back to my Catia here. I'm going to close that. I'm going to double click on this, but let me see if I can uncheck your TX and TZ, see whether it changes that. Yeah, it's still not. So let me do another one. Put the cursor here, right click, generate 2D display. Next, finish. I don't want the displacement in direction Y and Z. So let me see. Uncheck these things. Okay, uncheck these things. Select this point. This was node 2, the middle node. Okay, where I'm applying the load, and this one. The only thing is that I have not checked TX and TZ here. You say OK, and if you double click on this, you should get only only TY and TZ, and you do. Oh, I have to do these things one more time. Right click, format real, OK, and right click, options, standard options define, or the units defined, and now you can see there's only node 1 and 2, TY and TY. Now, just keep in mind that this node 1 in Catia is my middle node. Sorry, node 1 is my end node, and node 2 is my middle node. So the ordering kind of has changed here. So that's because I have no control over how Catia labels these. I have the control over these things. So, but the results look correct, and they are correct. Now, I challenge you to do the same problem, except that you have different initial conditions, different displacement, and see whether you can get it to work. Good luck.